Welcome to this explainer. We all love a perfectly conditioned room, right? But today, we're completely bypassing the thermostat. We're diving straight into the rigorous math and the invisible architecture that actually dictates indoor comfort. We're talking about the exact formulas engineers use to manipulate the very air around us.
To really unpack this, we're going to follow the life cycle of a breeze through 5 stages. We've got the science of airflow, mastering heating and cooling, moving air efficiently, the invisible role of moisture, and finally, measuring HVAC capacity.
All right, let's jump right into part 1, the science of airflow.
So how exactly do we measure invisible moving air? It's a massive foundational engineering challenge. And the solution really comes down to capturing physical volume over a specific amount of time.
You're probably familiar with this one. The standard metric here is CFM, or cubic feet per minute. This is literally the bedrock of the entire HVAC industry. It's the absolute physical quantity of air passing through a duct network and blowing into a space every 60 seconds. And the beauty here really lies in the formula itself. Airflow equals area times velocity times 60. We're basically just translating geometry and speed into volume. You take the cross-sectional area of the duct, factor in the velocity of the air, and then scale those feet per second up to minutes by multiplying by 60 to get our CFM. Moving right along to section 2, mastering heating and cooling.
Now that we know our air volume, we have to actually treat it. This brings us to the sensible heat formula. To find your sensible load in BTUs per hour, that's our Q variable, you take the constant 1.08, multiply it by our CFM, and then multiply by delta T. That 1.08 is a constant derived from the standard density and specific heat of air, while delta T is simply the temperature difference between the current room and the conditioned supply air.
But here's the thing, temperature is only half the story. The absolutely crucial point here is separating sensible heat, which is what you actually read on a thermometer, from latent heat, which is the hidden energy tied up in humidity. Sensible heat makes you say, wow, it's 90 degrees in here. Latent heat makes you say, man, it is incredibly muggy. And an air conditioner, it has to fight both of those battles at the exact same time.
So, achieving true comfort means adding both the sensible temperature load and the latent humidity load together. Think about it. If an engineer only calculates for sensible heat, sure, the room might read 72 degrees on the wall, but it's going to feel like a damp swamp. Your total cooling load, or Q total, ensures the equipment has the raw power to handle both the heat and the moisture.
All right, section 3, moving air efficiently.
We've got the temperature and the volume sorted, but physically pushing that air requires serious mechanical effort. This is where we calculate brake horsepower, or BHP. The formula relies on multiplying our CFM by static pressure, and then dividing that by 6356 times the fan's efficiency constant. Static pressure is just a resistance the air faces inside the ductwork. It's kind of like trying to drink a really thick milkshake through a tiny straw. The harder it is to push, the higher that static pressure goes, and the more brake horsepower the motor demands to get the job done.
And this math right here brilliantly illustrates why routine maintenance is such a big deal. Keeping filters and coils clean isn't just some nice suggestion. It directly impacts these friction and power equations. A dirty filter acts like a literal wall, spiking your static pressure. And when static pressure goes up, the brake horsepower required goes up right along with it. That means your system works harder, chugs more electricity, and burns out way faster, all because of a little dust.
Let's dive into section 4, the invisible role of moisture.
We touched on latent heat just a minute ago, but the defining metric to look at here is relative humidity. Expressed as a percentage, relative humidity dictates whether a room feels pleasantly cool or just uncomfortably sticky. And it's not just about how much water is floating around in the air, but how much water the air is physically capable of holding at its current temperature. Warmer air can hold a lot more moisture than colder air. The math behind this is actually surprisingly elegant. This straightforward equation, dividing actual vapor pressure, PV, by total saturation pressure, PWS, and multiplying by 100, is the hidden architecture of human comfort. It literally measures how full the air is with water vapor. If the relative humidity hits 100%, the air is totally saturated. Your sweat can't evaporate at all, which is exactly why high humidity feels so incredibly oppressive.
So, how do we actually pull that moisture out? Well, when air passes over a cold cooling coil inside an AC unit, this formula tracks the specific latent heat being removed. It compares the humidity ratio of the air entering the system, W in, against the air leaving, W out. By multiplying that difference by the CFM and the constant 4840, engineers can precisely calculate the latent energy, the actual raw water weight the system is pulling out of your air. You're basically quantifying condensation.
Finally, Section 5, Measuring HVAC Capacity.
So how do engineers actually size the heavy equipment needed to handle all of this moving, treated air? In an HVAC world, we use tons. But we aren't talking about physical weight here. We convert standard heat energy, BTUs per hour, into cooling tons simply by dividing by 12,000. Fun historical fact for you, before modern air conditioning, people used massive blocks of ice to cool buildings. 1 ton of AC capacity is mathematically equivalent to the heat energy required to melt 1 literal ton of ice over 24 hours. And that just happens to be exactly 12,000 BTUs per hour.
Because of this math, tonnage scales perfectly linearly with BTU capacity. It's easy to see how a tiny half-ton window unit handles 6,000 BTUs, while a massive 5-ton residential system easily crushes 60,000. When an HVAC tech tells you that you need a 3-ton unit, they are mentally running these exact thermal equations in their head to ensure the machine has enough thermal muscle to satisfy all the CFM and latent heat variables we've been talking about.
And of course, because this is a global engineering discipline, translating between metrics is just a daily necessity. Whether bridging CFM with cubic meters per second or converting tons of refrigeration into kilowatts, these conversion constants are what keep the math universally and perfectly aligned anywhere in the world.
Look around the room you're sitting in right now. The air you're breathing has been calculated for volume, balanced for sensible and latent heat, pushed against static pressure by a calibrated motor, and dehumidified over a dynamically sized coil. So the next time you feel a cool breeze indoors, you'll know exactly the mathematical symphony making it possible. But it begs the question, if this much math goes into just your air vents, what kind of complex engineering is secretly running your plumbing or your electrical grid? Thanks for joining me on this explainer, and keep staying curious.